Good morning, everyone. Welcome to our Cloud OnAir webinar from Google Cloud. We are hosting webinars every Tuesday. My name is Priyanka Vergadia, and today I will be taking Lisa with us and talking about Machine Learning 101. You can ask questions anytime on the platform, and we have Googlers on standby to answer your questions and during and after. So with that, let's get started. Lisa, over to you.
Hi, I'm Lisa Quera, and I'm a machine learning specialist in the customer engineering team. And hopefully what we'll accomplish together today is a sense of what machine learning is, what are some of the decision parameters around it, and how you can make it useful in your business processes to solve problems and capture opportunities. The first thing we need to do is establish some terms. So artificial intelligence is the science to make things smart. So I often actually prefer the term augmented intelligence, right? Because you're adding a layer of smartness to things. Machine learning is a way of teaching machines how to solve problems on their own, right? You're enabling them to learn and be smart. And then deep learning is a subset of that, which is some techniques to do machine learning. Now, this is the really important part, right? Is that this is a new paradigm. We've spent decades in a very controlled way teaching computers in a very explicit rules with programming language. The new paradigm is to help the machine learn from examples. So we're not controlling it from the top down. We're letting patterns and rules emerge from the data itself.
So Lisa, this sounds really, really simple when I look at it and this example.
Right.
Is it really that simple?
No. It's not. There are several deep learning approaches that can get pretty technical.
Yeah.
Today, because we have such a diverse audience, we're going to do our best to make sure that what we're talking about is accessible to everyone and is applicable across industries, right?
Yeah.
So let's first look at supervised learning, which is probably the most common thing that people understand.
Are we going to look at an example, an exciting one?
I am going to use one of my favorite examples because I'm going to use training a dog.
Oh, yeah.
Because it's actually not so different for a dog to learn from a machine to learn, and you'll see why pretty quickly.
Yep.
With supervised learning, what you're doing is you're providing input and output examples. So you're not only providing the input data, but you're also providing the targets that is associated with that. Now, if you think about applying that to training a dog, right? You help the dog understand the connection between a command and an action. And when you make it very explicit, right? So you tell them sit, and then when they sit, they get a treat. So they make that very explicit connection between the command and the target action.
Right.
And you do that over many, many, many examples.
Right.
And you guide them along the way as they get close to it. You know, you give them feedback and you help them adjust to creating that outcome.
Right, right.
Now, unsupervised, if you think about how supervised learning, you can probably guess how unsupervised learning works, is you have the data, but you don't provide those labels. You don't provide that target. Now, again, think about how a dog might learn. A dog can learn from observing you. They watch you day in and day out, and they observe from those examples of your behavior and come to their own ability to predict what comes next. So if I pick up my keys and the leash, he gets excited because he's able to predict that he gets to come.
Yeah.
But if I pick up the keys and I don't pick up the leash, you can see from the body language that he has predicted he has to stay home.
Yeah, sad.
Now, we didn't teach him that. That was something he learned. It was unsupervised learning from observations of data points. Now, reinforcement learning is a little bit more like supervised learning, except that the reward is delayed over time. So in reinforcement learning, you have a state, you have actions, and then you have a delayed reward. So we're going to stick with training our dog, and this time we're going to train our dog on a full obstacle course instead of a single command. So as the dog is running through and having a point of being, a state at any point in time along the obstacle course, we provide verbal feedback for either doing the next action, being a legal action or an illegal action along the course. And we guide them with that verbal feedback until they get to the win at the end when they get that reward. So reinforcement learning is feedback guided along the way until you get to the successful outcome. But that successful outcome is delayed a bit.
Okay, that makes sense.
Now, we use machine learning in everything we do. Sundar calls us an AI-first company, and what he means by that is that we try to use machine learning in every possible way to enhance our customer experiences and make our products better. And so if we think about some of the techniques that we just talked about and how they might show up in some of our products, let's take Google Photos. Would that be supervised or unsupervised, do you think?
Supervised because it's got labels?
Exactly, right? When you upload your image and we automatically suggest labels for you, that's because we trained it on a data set of hundreds of millions of images with the associated labels. And so that's able to I think there's, what, 20,000 labels that we associated with that?
Yeah.
So it's able to make your life easier by having the machine take on that load. Now, Gmail, Smart Reply, what do you think? Supervised or unsupervised?
That is unsupervised because there must be a large amount of data that it's looking at,
Right.
and then not just data from my emails and my replies, but also from all the other emails and replies, and then identifying what are the patterns for the reply. So I would say unsupervised.
Exactly, right?
Yeah.
It's identifying patterns from massive amounts of data, because trying to come up with the input-output examples for every possible permutation of language would be really hard. So that's a great example of using unsupervised learning. And then everyone's pretty aware of the big AlphaGo win against Lisa Dole, with the global champion in Go. And the AlphaGo won 4 out of 5 games. And it did that by playing hundreds of millions of games and getting feedback along that process. But we don't just use it in our own products, right? But we use these models together, right? So one input is often the output to another model, because a model solves one problem really well. But most business processes have multiple tasks along the way, right? So you have to have models work together. And here's a great example of the Vision API being used to capture the text from an image and then passing that to another model with the Translate API to convert that text to another language.
I just had a question. Can you combine, like in this case, we're combining 2 models together, but how many of these models can you actually combine together? Is there a limit on this?
The limit wouldn't be from a machine learning perspective. The limit would actually probably be more from your infrastructure perspective, right? So the networking or the compute power behind it to pass those inputs and outputs along the process. So how long would that chain be, right? So if you needed fast latency, then you'd probably have to limit the number of models that you use. But that's not a machine learning question. That's more of an infrastructure question. So you just have to think through your business process and think, which tasks can the machine enhance along the way? But we're also using machine learning to help other people do amazing things. It's not just about products and services. It's also about trying to use machine learning to make things better for people.
Yeah, so this one's actually really close to my heart because I'm from India, and I have seen a lot of rural places in India that do not have access to doctors or, say, good doctors. But what Google Brain has done is they've built this software based on machine learning, and there's this model that identifies when you feed retina scans to this model, it identifies a disease that leads to diabetes. And that eventually leads to people not being able to see. So that is pretty huge. So this model can take these retina scans and identify whether somebody has that disease or has indicators of that disease, and then at that point it tells the or alerts this person to actually go see a doctor. And to me, that is huge. Now I can look into my phone and just identify that I might have a problem and I should go see a doctor. Is huge when I don't have a doctor around me. And somebody's telling me I should go do that, that to me is huge.
It is. Right? I mean, if I had my eyesight saved by looking into a phone camera, I think I would feel it's pretty magical. Right? And that's the big myth of machine learning, that it's magic. And I hate to disillusion you because we'd all like to believe in magic, but it's just math. It's just linear algebra and calculus combined to transform inputs into outputs. And here's another really key concept we want you to walk away from today, that machine learning is the process of algorithmically finding patterns in data. And we're going to keep, that word patterns is going to keep coming up, and we're going to keep coming back to the data, because I want you to think about the data as the knowledge potential of what your machine can learn.
The concept of machine learning has been around for a long time, and the concept in general for deep learning, I think, has existed since like 1960s.
Yes.
So one of the questions I had, and I'm pretty sure from the audience as well, is why is it that it's so important now, and why is it that people are working towards it now much more and are getting excited about this much more now versus like in the past?
Well, there's three key enablers, right, that are making all the difference now. Because you're absolutely right. A lot of this isn't new. Now we're doing new things now, and we're pushing the boundaries of knowledge all the time. But one of the biggest factors is the data, right? 90% of the world's data was generated in the last 2 years, right? And it's coming from everywhere, right? It's structured, it's unstructured, it's coming from the web, it's coming from social media, it's coming from ERP systems and CRM systems, and it's coming from Internet of Things and machine sensors and phones, and just a million of different options for bringing the data into your world and representing human reality via data points. Now, a lot of that data just sits there passive now, right? We're not doing enough with it because it might be in some format that we don't know how to work with, but you can transform that and start pulling insights and predictive capabilities out of that data set. But if you didn't have these giant things to learn from, enough examples to learn from, we wouldn't be able to build these great models. And the other aspect, of course, is the computing power, right? You can't work with that much data and these different models without the compute power. Right. In 1961, when the multi-layer perceptron was originally discovered, the supercomputer at the time, didn't even hold a candle to your phone today. So it couldn't do anything with that knowledge. We couldn't explore it enough, right? Yeah. So now we can. But of course, what does it start with?
Data.
Data. It's not who has the best algorithm who wins. It's who has the most data. And that's coming from a co-founder of Google Brain and a former Stanford professor. Now, why do we agree with him? Why do we think that that's so true, right? The data determines what the model will learn. Remember that it's the knowledge potential, right? If the data does not accurately, completely, and fairly represent the problem environment, a model cannot find the optimal solution. Now, when we talk about completeness, what are some of the things that come into that? Variety, right? So you can't just train it on examples of a user behaving in one way or just a single user, right? You need a variety of users, and you need those users to behave in a variety of ways. So diversity of your data set is really important. And then, of course, number. So that's the complete part, is that we need to make sure that you have a lot of it. Now, the second part is the quality of the models. So yes, the ideas have been around forever, but without the ability to test those ideas against large data sets and with a lot of compute power, they couldn't identify the best techniques, right? And now we can. Right. So let's start to drill into how models work, and we're going to try to keep this at a good level.
Are we going to go into math and formulas and stuff?
A little bit.
Okay,
awesome.
Bit. Well, fun part's coming.
But the important thing, again, conceptually, right? Conceptually, we're applying weights to features to calculate an output, right? So if we think about how a human makes decisions, creates an output, we also do it by applying weights to features, right? Let's think about looking for an apartment, right? And how much weight do you apply to the parking space, right? How much do you apply to the location, right? These are features of the apartment that you then apply different values to in order to predict which one will satisfy your need, right? Same idea with machines. Now, the difference, of course, is that machines only work with numeric data, right? So we have to convert any of our data points into numbers to work with. So if we have an image, this one is from the CFAR10 data set. So it's a very common data set used to test out models, so you can compare models across different architectures. So you take the image and you convert it to an array of the 32 width by 32 height by the 3 channels, red, green, blue,
Okay.
right? And you end up with 3,072 numbers in total. Each of those numbers representing that pixel feature, right? So that becomes the x in the function, the input data.
Right.
And then we have these weights that we start to assign to each of those pixels to understand its salience. How important is that feature to calculating the output? Right? And in the end, you end up with the 10 different labels that are in that data set, and you're able to identify that that's a cat.
Awesome.
So let's think again about this neural network, right? We have the concept of the input and the weight, and we start to do a matrix multiplication. Key term that we're going to come back to later when we talk about the power of hardware, because matrix multiplications are compute intensive. But we have our input, and then we assign our weights, that's a product, and then we add them together across the different weighted features to come up with an output. We run that output through an activation function. Think of the activation function as being a sorting mechanism, right? So you're sort of sorting signal from noise.
Yep.
Which of these features contributes the most to determining the output, right? And once we have that, then we do a prediction. So we calculate our first guess. Now remember that we start out knowing nothing, so we randomly initialize the weights because we don't know anything.
Right.
And then we make our first prediction, which is probably pretty awful. We compare it with the label, and that error, that difference, is what we use to guide how we're going to update the weight, how we're going to adjust it, right? And then we keep doing that iteratively across all of these learning runs, all of these different examples, until we have finally adjusted that weight to the point where it's a very accurate representation of the knowledge potential and the reality that we're trying to capture to solve the problem or capture the opportunity. Now here is a supervised learning problem, a simple binary classification for vision, but this is the deep part, right? So now you have your neural network, you have your weighted outputs, right? The first layer is just capturing very simple concepts, like maybe shading, right? You then pass that to the next layer, so the outputs of one layer becomes the inputs to the next, and that next one refines the concepts and turns those shading into like lines or shapes. And then it keeps doing that along the way so that the lines and shapes become eyes and mouths. And then the eyes and the mouths and the ears become cats versus dogs. And then finally you have that output, understanding the classification and capturing the label.
Yeah.
Does that make sense?
It does. It does. I think it'll be good to go and visualize this a little bit for people.
Right.
Yeah.
Okay, so let's see an example so that you can start to see that connection between data and output.
So we've chosen this example today mainly to guide us through the process of how machine learning actually works and how a machine actually takes the inputs, gets trained, evaluates, and then predicts. And I think AutoML vision is a great example because it helps you visualize. There are images that are going into the system, so it helps you learn and understand what is actually happening. So that's the sole purpose of taking this as an example. And we're going to consider ourselves to be people who are learning about clouds to understand the weather patterns. So let's consider ourselves as scientists and in identifying weather patterns. I have taken some examples here of images of different clouds, and they're also labeled with different labels of the types of clouds. Now, when you hop into AutoML Vision interface, the first thing you see is the images, which is obviously Lisa has emphasized enough about the fact that data is really important. So
I have never emphasized that enough, ever.
So we go with this, as soon as we enter into the interface, we end up putting data in. And in this case, it's the images of the clouds. Now, there are two ways to enter data in. One is through Google Cloud Storage. You could create a CSV of your links to all the images associated with the labels. And once you have those, you could upload that CSV into the interface, and you would have all these images loaded up in here. The other way to upload images is to just click on this Add Image button and just use the user interface to actually upload those images. So those are the two ways to get your data into the system. Once you have the images in, you'll also be able to filter and see the number of images in here. I think this is important. If you see, we have large number of images for Cumulus and Cirrus and also oh my God, I can't even read it. So I'm just gonna avoid it, not reading. So the last three, we have a large number of those, and then and you can see the ones with the altos are a little bit less. And we'll come back to this. That's why I'm pointing this out. So you have this data set. Now, once you have the data set, you have the next step, which is to train your model using this data. We've already obviously trained this model, so we're not going to do that today. But when you do it for yourself with your own image data set, you will be able to use the Train tab to train your model, and then you could use options to train it for a longer period of time or a lesser period of time. And there are advantages to training longer because the model would learn better. Is there anything else you would like to add, Lisa, here?
No, I think that's the key point in the compute time is that this is also, remember, compute hours. It's not necessarily linear time. So the two models that we've trained, you can see one has a 1 hour compute time, but I believe that was probably about 10 minutes, and I think that the second model, even though it says 2 compute hours, because of distributed processing and parallel computing, that I think was only about 15 minutes.
Okay. Yeah, so make sure you select the time depending on how good you want the model to be and how well trained you want it to be. So after the first two steps of getting the data in, training the model, now we are at the evaluate step, which is where you're actually able to see the metrics. And how do you see the metrics? There are multiple different metrics that you can see, but the one that I like to highlight and point out is the confusion matrix. No, it's not confusing. It's really just and you'd understand why it's called confusion matrix in just a little bit. So when you, let's take a step back before we dive into confusion matrix. When you add images into Cloud AutoML Vision, what it does is it separates out your images into training data set and test data set.
And it does that automatically, which is great.
Yeah, so you don't have to do any of that. You just upload and it'll take care of the separating for you. And for machine learning, for your model to train on a specific data set, and then it's important that you have a certain test data set ready to train the model that the model has never seen before.
Exactly.
And what we're doing here, this confusion matrix is taking that test data set and then predicting and then showing you how accurate that predictions were. So in this case, we can see that it was 90%, 94.7% accurate for the first two of them, but then we see less accuracy on the ultrastratus one, which was 46.2%. Now, you also see that 23% of those were identified as Cirrus. So this could, and now this allows us to actually go into our data set and see what the problem might be.
Right.
And goes back to Lisa's earlier point, it depends on how good your data is and how much data you have supplied to the model. So if you remember, when we were looking at the images and their labels, the ones with altos were very less. So we had very few examples of those in there. So that's why our model is probably getting confused. So we may need more data to support those examples. And I think that is the important point that we wanted to come across, that data is obviously the key. You want to make sure that whatever you want your model to learn, you've provided enough examples of that in the data set for it to learn from.
Yes.
right? And then the last step is obviously prediction. And we provide you, you can see here the curl command for the REST API. The AutoML Vision would generate a REST API for you that you could use to apply into your, to bake this model for predictions into your, either your website or your mobile application, whatever it is that you want to use this model into. Hopefully that was a good starting point in terms of seeing how all the steps work, from putting the data in to training to evaluate and then starting to predict. With that, I'll pass it over to Lisa to give us some more information on models.
Yes, I mean, I think that the important point that we wanted with that was this connection between data and quality.
Yeah.
Now, parameters are what the model learns to use to represent that knowledge potential. Hyperparameters guide how well or how poorly the model learns.
Hyperparameters, Lisa, has always been something that I have struggled to understand. So if we can take some examples to help our audience learn this.
Yeah, hyperparameters, I've always thought that they should have come up with a better term.
Right.
Because it is a little confusing, the what versus the how.
Yeah.
But a couple of my favorites are learning rate. So the learning rate controls how much you adjust that weight during each learning iteration. So as you're going through the examples, how much do you change that weight up or down to reflect the new information you got from the latest example, right? The latest error signal that guided how you changed it. The learning rate says how much you change it, right? So I want you to imagine that you have a huge stack of books to get through to learn something. Now, you could just skim through them very quickly and get to the end, right? But you'd probably miss something important. And you'd certainly miss the optimal solution. Or you could go very slowly, line by line, take notes on each one. But then you might only get through a third or half of the books in the time allowed. So you would never get to a solution. You need to find the right learning rate for yourself as you go through those books. The model needs the right learning rate to understand how fast or how slow to adjust those weights. If the adjustment is too big, then it could jump right over the optimal weight. But if it's too small, it could take too long and never converge because it'll just run out of compute time. Right? So the learning rate is really important. Another one that I like is the dropout rate. And I like that because it seems counterintuitive, but it's actually really in sync with how humans learn. So the dropout rate is intended to prevent something called overfitting.
Okay.
A model that overfits to the data set is a model that has memorized the data. So it can't actually predict on anything new. It would totally fail on that test set, right? Something that's never seen, it fails.
Right.
So we introduce a dropout rate to basically make the learning harder. Periodically, we randomly zero out some weights.
Just like how a human, just like how I forget after I read something and 10 days in, I need to go back and read it.
Exactly, right? But then you retain it more
Right.
if you have this interspaced learning, right?
Yeah.
Well, this works the same way, right? So dropout rate is another really important hyperparameter that can impact the quality of your model. So hyperparameters are the how, and the different combinations really make a difference in terms of data science productivity. Now, the AutoML vision that we saw is created by a model. So it's a model creating a model, and that's Neural Architecture SearchNet. And you'll notice that it's not only more accurate than the human models, and these were created by some of the finest mind in the AI community. You know, you've got the best of Google and the best of Facebook creating these kind of things. And you'll notice that the machine one beat them.
Yeah.
And not only did it beat them in accuracy, which is the quality of the model, but also the operations, so the amount of compute time it took, and the parameters. It's smaller, so it'll be able to be served faster. So it's not only more accurate, but it's more efficient.
Right.
The last part of the why now that we want to cover is the compute power, right? So the ideas aren't new. The data we've been getting for a few years, but it's this ability to process massive amounts of data with big, complex models and a variety of hyperparameter combinations that needs this kind of compute power. Right?
Yeah.
And these models can be really large, and these data sets can be so large, it can literally take months to process those big data sets through the big models and to optimize the hyperparameters along the way. So for a data scientist to wait months for a result is a huge productivity impact, right?
Yeah.
So if we could experiment faster, then we could create higher quality models.
Right.
And the more compute power we have, the more we can distribute the training, and the more we can optimize each training session to get that quick iteration and more experiments that we can run.
So hardware accelerators basically help us do the training faster, right?
Exactly, right? Because they're optimized for that, right?
Right.
So here is training a large-scale machine translation model, and you can just imagine the size of that model because
Right.
language is so complex. The knowledge potential that a machine would have to capture would be gigantic.
Yeah.
And in this case, it would be 24 hours being parallel processed across 32 GPUs. But because tensor processing units optimize that matrix multiplication we saw earlier, and it's really specialized for deep learning and for the math that is unique to deep learning, you can compress that to an hour and a half. So imagine a data scientist waiting 24 hours to get the results of an experiment and make another adjustment, or an hour and a half.
Yeah.
Right? Big productivity increase.
Now, I think we have learned the model and the way models work and the math behind it a little bit. But I think it'll be good for us to understand what are the things to keep in mind as people start to think about machine learning and applying it into their projects.
Well, the first thing is that the model is really, it's the most fun piece, but it's a small piece of the overall solution. Data. So data collection, data management, data understanding with exploration and analysis, and different feature engineering to make sure that your data is accurately capturing either the problem that you want to solve or the opportunity you want to capture. You need to represent it in the data, and that's going to take a huge amount of effort. The model then is a pretty small part of it, but what's important is once you have that model, you want to use it in your business process. So that's called serving the model, creating the predictions. And you want to make sure that you're retraining it periodically, so you need to monitor it for its accuracy because it can degrade over time if the reality that you're capturing is actually changing.
Right.
So all of these are pieces that you have to think about when you're wanting to use machine learning in your business process. Now, some things to consider are please start simple and then add complexity only as needed. So try some of the pre-existing models like Cloud AI APIs. And if that's not getting you what you need, then try an AutoML service where you can make your more domain specific by tailoring it with your own data set. Yeah. If that's not getting you what you need, you can try something called transfer learning, where you learn from another model to jumpstart your own custom model. And then finally, build a custom model with a custom data set. But that will, of course, take the highest skills level and the most amount of time. So you want to do that only when it adds real competitive differentiation for you. See what you can do with what's already available first.
Yeah.
Now analyze your data to ensure you're accurately and fairly representing the reality you want to be learned. The data is your knowledge potential, so make sure you focus on getting that right. And then make sure the data features you use to train the model are available when you want to use the model. So when we talk about accurately representing environment, let's think about predictive maintenance for a moment, when you might have machine sensors in the field, but they're really impacted by the weather. So you want to use weather data to help make your model smarter. You want to increase that knowledge potential. So you use a weather data set to train your model along with the sensor data. But at the time of prediction, will you have that weather data available, right? You need to make sure that what you train is also what you have when you want to predict.
Right.
Next steps, there's so much more to learn, and I really recommend starting with the machine learning crash course that we have on our site. We've also collaborated with Coursera to create data engineering and machine learning classes. There are tons of tutorials available on the Google Cloud platform. And as always, there's Google search for any topics or white papers that you might be interested in. I hope we've piqued your interest on some things today.
And then if you already have something going on around machine learning that you would like some help with from our teams, then we do have Google Cloud account teams that are available to help you with any of your projects. So reach out to them. And then once you reach out to them, if you do require professional services, and we have very high quality partners that can partner with you on your projects as well. So we can bring them in and our professional services in as needed for your project. So make use of these resources. And let us know what you're doing in machine learning. All right, so we're going to switch to questions now. And
we'll be back in less than a minute.
All right, everyone. Looks like we have a bunch of questions from the live audience. So we'll ask those one by one and have Lisa answer them. The first one here is, data seems to be very critical to machine learning. How and where do I get enough data to build an accurate model?
Well, first of all, thank you for listening. And how and where you can get enough data to build an accurate model is complex because it depends on your particular situation and what problem you're trying to solve. But one thing I would say is you don't have to just look inside your own organization to find data. Don't forget that you can enrich your data set with other external options, right? So there's some big query public data sets that you can explore, right, to see. Those are also great for prototyping and exploring different model options while you're gathering your data inside the enterprise, because sometimes it can take quite a while to put those data sets together, and it might be different people working on the data and the model. So the model folks can be testing with some public data sets while the data folks are getting all of that collected.
Right.
So I would look at BigQuery public data sets. Kaggle has a lot of open data sets. Academics are often sharing their work and publishing not only the model code that they do, but the data sets they use to train that code. So those are options outside of the enterprise. And then inside the enterprise, just think about the problem you're trying to solve and what do you believe most accurately and completely represents that problem.
Okay. That's very helpful. So the second question here is, can I still build a good machine learning model with a small amount of data?
Again, it depends. The things that I constantly repeat are patterns and data, and it depends. But you can use transfer learning, because transfer learning enables you to use a sort of jumpstart model that has already been trained on a massive data set. And then you can customize it with a small amount of data. So when we think about the example that Priyanka showed us with AutoML Vision, that was a tiny data set. There was 1,800 examples, right? Really small, which normally we would say no way can a machine learn from so few examples. But because it uses the NASNet architecture in the background and a trained model from that NASNet, it's able to just tailor the last few layers of the model to customize it for your domain specificity. So if you only have a small amount of data, then you need to start looking at transfer learning options.
So the key to this is going back to some of the things to consider points that you made. Start from what's already available, then look at AutoML maybe, and then start to look at transfer learning. And then if none of those do the job that you're looking to do, then you build your own custom model.
Exactly. And there's things that you can do to expand that data augmentation options. But again, bigger is better when it comes to the data part. Which leads us to the second question.
Third, last question, is bigger always better for models?
Well, there's a trade-off between speed and accuracy. So it depends on how you define better. What is it that you want to optimize for? If you want to optimize for accuracy, then it can be that bigger is better. But remember that concept we talked about, overfitting?
Right.
Overfitting means that it can memorize. If your model is too big and complex, it might just memorize things and not be able to generalize.
Right.
So sometimes you need that sort of little bit of error in the mix, right? And then the other thing you need to think about is not just accuracy, but speed. The bigger the model, then the slower it will create the inference. And if latency is an issue when you're using that in your business process, then a smaller model might indeed be much better, even if you do sacrifice some accuracy.
Okay, well, that's amazing. Thank you so much, everybody, for listening. Stay tuned for the next session. Bring your teams closer together with G Suite's meeting solutions, and thank you.